Hi, everybody. It's Professor Mitchell, continuing with Chapter 7. Now we're going to look at Section 7.2 on natural logarithms. This, I think, will be a two-part video. Otherwise, it would be way too long. All right. So there are two different approaches to teaching calculus. There's what's called early transcendentals and then late transcendentals. What we do at our college is late transcendentals. The transcendental functions are things like natural log of x, e to the x, inverse trig functions. And what late transcendentals means is that we don't do a lot with those functions until Calc 2. Now, there are advantages and disadvantages to that approach, but my favorite advantage to that approach is that I get to really properly define what natural log of x is in terms of calculus. All right, and here it is. This is the definition of the natural logarithm function. That function is given by natural log of x equals the integral from 1 to x of 1 over t dt. Notice that x has to be greater than 0, and that's because the function 1 over t is undefined at t equals 0. So we would have a little problem if we tried to define this integral or this function for x equals 0 or for x equals any negative number. Okay. Now, I will admit it takes a little effort to wrap your brain around this kind of function, this sort of integral function, where the independent variable is one of the limits of integration. I believe in your Calc 1 review quiz, I do include a few problems like that because I want you to review those. But here's a nice picture that kind of explains it. So here in red, you have the graph of y equals 1 over x. So there are two different scenarios. Let's talk about the simpler one first. If x is greater than 1, then the natural log of x gives you this area in blue. And what this blue curve is, this is the graph of y equals natural log of x. So at this particular value of x right here, this value, it looks like, well, the y value, which looks like 1, is equal to the area. All right, it's saying that this blue area is also approximately 1. Notice if x equals 1, this function just turns into the integral from 1 to 1 of 1 over t dt. And hopefully you remember from Calc 1 that whenever you integrate a function from a to a, that is automatically 0. And then if x is between 0 and 1, for example, let's say x is 1/2, then you would have the integral from 1 to 1/2 of 1 over t dt. And another Calc 1 property of integrals is that the integral from 1 to 1/2 is the opposite of the integral from 1/2 to 1. So what that means is that if x is between 0 and 1, then the natural log of x is going to be a negative number. It would be the negative of this area here. Okay. So in Calc 2, that's how we define natural log of x. And we're going to build sort of everything that you already learned about natural log of x in pre-calc using that definition. All right, here are some typical two-place values of natural log of x. I'm not going to read all of these to you. A couple of highlights. Of course, the natural log of 1 is 0, again, because the integral from 1 to 1 is 0. Natural log of 0 is undefined. I just noticed a little typo here. I don't think I noticed this any other time I've taught Calc 2. This should be a t, all right, which is what's called a dummy variable. You're really not supposed to have the same variable here and here. So change that to a t. It should be 1 over t dt. How were these values determined? probably using a process called numerical integration. And right off the top of my head, it's been so long since I've taught Calc 1, really, or Calc 2. It's been a few years that at this point, I can't remember whether we cover numerical integration in Calc 1 or Calc 2. So, well, if we cover it in Calc 1, then you've already heard about it. And if we cover it in Calc 2, you will hear about it later. All right, let's talk about the number E. You've seen this number before. The number E is that number in the domain of the natural logarithm satisfying natural log of E equals 1. So if we go back to that picture we were looking at a little while ago, it looks like this value of X might be E, because I'm noticing that if I follow this up to the natural log curve and then go over to the y-axis, I hit it right about 1. And you already know from your pre-calculus class that the approximate value of E is about 2.718. All right, so more about E later. All right, now we come to the derivative of y equals natural log of X. The derivative with respect to X of natural log U, so I'm giving you the chain rule version of this derivative rule, is equal to 1 over U times du dx. All right, so if this was just the derivative with respect to X of natural log of X, it would just be 1 over X. Okay, let me jump over to the tablet for a second. All right. So if I were to take the derivative of this function with respect to X, all right, then I would be taking the derivative. Remember, U is a function of X, so it might be helpful to just write this as U of X. Okay, so then we would have the derivative with respect to X of integral 1 to U of X times 1 over t dt. All right, so by one of the parts of the fundamental theorem of calculus, the derivative of the derivative and the integral basically cancel each other out. And how it works with the chain rule version is that you're left with 1 over U of X times the derivative of U of X. And we can make that look a little simpler by just writing 1 over U times du dx. Okay, so this is an extremely useful differentiation rule. Let's go back to presentation. Okay, whoops. Okay, now I just want to point out this is not as useful of a differentiation rule. It will be an extremely useful integration rule. And I'm going to resist the urge to prove this one to you. Let me get this explanation out of the way. So I am a math major. I recognize that not all of you are math majors. What math majors love to do more than anything else is prove things. Engineering and science majors don't necessarily care about seeing the proof of things. So I am going to strike a balance with you. There are certain things that I am not going to be able to resist the urge to prove, but I will limit it as much as I possibly can. So for example, I will spare you the proof that the derivative of natural log absolute value of X is also 1 over X. Notice that that's good for all X not equal to 0. Okay, but I am going to prove at least one of these properties to you, and I will limit it to 1. You're familiar with these properties from pre-calc. For any numbers b greater than 0 and x greater than 0, the natural logarithm satisfies the following rules. You have the product rule, which says that the natural log of b times x is equal to natural log b plus natural log x. You have the quotient rule, which says natural log b over x is equal to natural log b minus natural log x. You have the reciprocal rule, which says natural log of 1 over x is just the opposite of natural log x. And then you have my favorite, the power rule, which says that the natural log of x to the power r, you just grab this exponent and you go. If you took me for pre-calc, you used to hear me do that all the time. And that comes out to r times the natural log of x. Now, there's a little note attached to this that says that's true if r is rational. It's actually true for any real number r. It's just that if I were to prove this to you right now, based on what we've covered since the beginning of Calc 1, I would only be able to prove it for rational exponents, but it is true for any real exponent. So I'm going to go back to the tablet and show you the proof of rule number 1. I just can't resist. This is pretty cool. Okay, so right here is the product property. I'm going to prove this to you in just a second, but I want to talk a little bit about how I'm going to do that. So think back to Calc 1, and suppose that I said to you, I'm thinking of two functions, call them f of x and g of x. And I said to you that f of x and g of x have the same derivative, What can you say about the functions f of x and g of x if they have the same derivative? Are they the same function? Well, maybe, not necessarily. The best thing you can say about two functions that have the same derivative is that they differ by a constant, okay? So here's what I'm going to do. I am going to show you the derivative of, let's build a little suspense here. First, I'm going to show you the derivative of natural log x, which you already know. The derivative of natural log x is just 1 over x. And now I'm going to show you the derivative of natural log b times x. Okay. So for this, I need the chain rule version of my derivative rule. Let me spell out for you what natural log b times x is. It is the integral from 1 to bx of 1 over t dt. So using the chain rule version of that fundamental theorem of calculus that you've seen me use once already, the derivative and the integral basically cancel each other out. What's left is 1 over bx, but then I have to multiply by the derivative of bx. All right, and of course, b is a constant. So what is the derivative of bx? It's just b, isn't it? Look what happens. We have 1 over bx times b. The derivative of natural log bx is 1 over x, just like the derivative of natural log x is 1 over x. These two functions, natural log bx and natural log x, differ by a constant. So I can say, therefore, natural log bx is equal to natural log x plus some constant. But now we have to figure out what the constant is. So let's plug in a number. Let's say x equals 1. That would give you natural log b is equal to natural log 1 plus a constant. And what is natural log 1? Natural log 1 is 0. So guess what? That mystery constant is natural log b, and we got it. So we'll do a big bold therefore. Better enclose this because I'm kind of running out of space. The natural log of b times x is equal to the natural log of x plus the natural log of b. And I think that is really cool, but of course I would, right? All right. So All right, here we are. And you have these other rules which can be proven kind of similarly. All right, so now we come to an example. And we actually do problems like this in pre-calc. We're going to express the following logarithms in terms of natural log 5 and natural log 7. These two logarithms. And then after we do that, we're going to use properties of logarithms to simplify this expression. And I think after we do that, we will wrap up this part of 7.2 lecture, and we'll do the rest in part 2. Just trying to keep the videos to a reasonable length. All right, so we want to write these logarithms in terms of natural log 5 and natural log 7. All right, so what I'm going to do with this is, let's write this as natural log 1 over 5 to the third. 125 is 5 to the third. Using the reciprocal rule, the natural log of 1 over 5 to the third would just be the opposite of natural log 5 to the third. And then using rule number 4, the power rule, you can take this 3 and go. So the natural log of 1 over 125 is equal to negative 3 times the natural log of 5. All right, now I've always thought natural log of 9.8 maybe is just a little trickier. All right, so here's what I'm going to do. I'm going to write that 9.8 as a fraction. Why don't we just write it as 98 over 10? Okay, now that's not super helpful until I simplify that fraction. 98 over 10 simplifies down to 49 over 5. Remember, we're trying to write this in terms of natural log 5 and natural log 7. So hopefully that triggers something. First of all, using the quotient rule, I can write natural log 49/5 as natural log 49 minus natural log 5. And then, of course, 49 is 7 to the second. And now using my favorite rule, the power rule, I grab that 2 and I go, and I get that the natural log of 9.8 is equal to 2 times the natural log of 7 minus the natural log of 5. And lo and behold, we have written natural log 9.8 in terms of natural log 5 and natural log 7. And that's going to do it for part 1. We'll see you in a minute for part 2.